Sayuj. But today is Pi Day, right? 314. So I feel as though we have to do a little bit of stuff associated with pi. And then I filled in a couple little things that I think will be interesting and fun for you as well. So let's start. What is pie? It's a dessert treat made of flour and sugar and often fruit. No. Yes, Mark.
The circumference divided by the diameter.
You win. If you take a circle and you were to figure out exactly the length of the diameter, and then you say, okay, now I'm going to pull that diameter out and wrap it around the outside, you'd find that you can wrap it a little bit more than 3 times, right? It'll wrap 3 times plus a little bit. And what that means is that pi by definition is the circumference divided by the diameter. That's what it is. That's what it means. And that's why it's an imprecise or an irrational number, because this perfect idea of a circle yields something that isn't a fraction. You're dividing a circular component by a straight linear length. But we can do a couple things with this. One, we can cross multiply and we can get that C is equal to pi times D. And you might know this as the formula for finding the circumference. You might also replace D, which is the distance all the way across a circle through the center, as 2r. So a lot of people use this as pi times 2r or 2 pi r. That's the way I always think about circumference. What about the area of a circle? In other words, instead of looking at the distance around the outside, what if I talked about the area of a circle, right? No, pi around. Just kidding. But yes, pi r squared is the formula for the area of a circle. But where's that come from? Like, I'm looking around the room and seeing so many people fighting the urge to snicker at that. Where's that come from? How do we know that pi r squared is the area of a circle? So let's say that we have a circle, and sure, we can treat it as a pie. We decided to slice it up into pieces of pie. And then I take out each of those pieces of pie and I lay them down. Here's one. And then I lay the next one in a pattern like this.
It'll be the same area.
It will be the same area because it's all the objects, right? But can we actually do something about finding the area of this, whereas we couldn't have done it with this? What shape is this kind of looking like?
Parallelogram.
Yeah, a little bit of a parallelogram looking thing. Hi, Haley. It's not quite a parallelogram, right? Because it's got this scalloped top that isn't like a straight edge. So let's make it a little bit more precise. Let's cut these slices of pie in half. So they're smaller now. And when we put these together, now instead of it being so slanted like this with a big wide arch here, it's going to be narrower. And we do the same thing. I did really poorly drawing this one, but you get the idea. And it's going to be more of these that fit in, and it's going to end up being not as slanted like a parallelogram. It's going to be straighter, right? And if I kept doing that again and again and again, reducing the width of these, eventually what I'm going to get is these things that are super, pretty much like lines, making up this shape. Now, if r is the radius of this shape, then this length is r, right? And this length is r, and actually going straight down to here is also r. But as I make these smaller and smaller and smaller, the edges of the piece of pie and this little radius going straight down get closer and closer and closer until here, they're basically just a string of a radius. Now, if this is a rectangle at this point, how do I find the area of a rectangle? It's not supposed to be the hard part. How do you find the area of a rectangle? Base times height, okay? So whatever this length is times this. We know that this is the radius of the circle. How long is this? Almost, it's half the circumference, right? Because I alternated, I put half on the bottom and half on top. So this part is 1/2 circumference. And if circumference is 2 pi r, then 1/2 of 2 pi r is pi r. So this length is pi times r, which means the area of this shape is base times height, or pi r squared. A little bit cool, right? Maybe not. I think so. So let's take it one more step here. Let's do some more proof. But I want to prove something that we've been dying to use all year long, and I've been forced to kind of do it without proof. Let's do a proof of the, can't spell, Pythagorean theorem. Proof of the Pythagorean theorem. What is the Pythagorean theorem? Really close. Remember that if it's a theorem, it should have a hypothesis and a conclusion. And I think you're right that a squared plus b squared equals c squared is the conclusion, but under what circumstances? If right triangle, it's got to be a right triangle. Does not work for acute, obtuse, equilateral, etc. And which parts have to be A, B, and C? Is A the area and B is the temperature and C is the color? No. A is the length of one leg, B is the length of another leg, and C is the length of a hypotenuse, the side opposite the right angle, the biggest side. So this is what we're going to try to prove. And by thinking about it as a theorem, we have a hypothesis where we start and a conclusion where we end up and say, done, we've proven it, QED. So I'm going to do a proof for you now. And as expected, I have to start with the hypothesis. I'm going to start with this triangle. Now, for my intentions here, what I'm going to do is I'm going to take this triangle and I'm going to do dilations of it. Okay. We've just been working with similarity. And do you agree that I can take this triangle, and if I take each of the legs and multiply them by something special, whatever it is, it'll still be a similar triangle, right? So if I take this side of A and I multiply it times A, and then I take this side of B and I multiply it times A, and this side of C and I multiply it times A. So these sides are now AA, AB, AC. Are these two triangles still similar? The ratio of all the corresponding sides is A. Okay, so like if I had a star to represent this angle and a star to represent this angle, they would still be congruent. They'd still have a right angle here. And I'll put a little circle in this one to show this angle. I don't know what the angle measure is, but these angles are the same. These angles are the same. These angles are the same. These sides are in the same proportion as those sides. They're similar triangles. Now I'm going to create another similar triangle. So it's got the same angles because it's similar. And this time I'm going to take my A, B, C, and I'm going to multiply them times B. So A, B, 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 C. Do it one more time. Any guesses what I'm going to multiply by? C is correcto. So I'm going to multiply this. I'm going to get A, C, B, C, C, C. And again, the triangles similar, so my angles stay the same. Now, among all these similar triangles, I'm going to grab this first one and I'm going to draw it down like this. And I know that this side is AC, this side is CC, this side is BC. Here's my right angle. Here's my star, here's my circle. Now I'm going to take this triangle, the yellow one, and I'm going to pick it up, translate it, rotate it, and set it back down right here. Sure, take the pass, please. And because I know that the hypotenuse of this one is BC, and this length is BC, they're the same. So I can get a little reflexive action going on there. They're sharing the same space. And this is going to be B times B, and this will be A times B. And my star is here, and my circle is here. And then I'll do the same thing with this triangle. I'm going to take my orange triangle, my smallest one, and I'm going to put it on right there so that this side is AC, this side is A times A, and this side is A times B. A, B, C. And because this is a star and this is a circle, what shape is this? If it's a rectangle, then it satisfies certain criteria. Let's be specific. What does it take to make it a rectangle? 4 right angles. Do we have a right angle here? Do we have a right angle here? Do we have a right angle here? We have a star and a circle. The star and the circle were the 2 non-right angles in the original triangle, which adds to 180, but you subtract the 90. And so what do the star and the circle add to? 90. So is this a right angle? Star and circle. Yeah. What about this star and circle? That's also right angle. So it's got 4 right angles. Is this a straight line though? Because it's kind of broken. Is it like, what's this star and this circle add up to? Plus a right angle makes 180. Isn't that a straight line? Therefore, this is a rectangle. You guys were right that it's a rectangle. If it's a rectangle, what do you know about opposite sides? They're parallel and they're congruent. So if this one's AB, this one's AB as well. That's not a surprise. How long is this side? Also known as C squared. How long is this side? A squared for this part, B squared for this part, and we're adding them together, aren't we? If it's a rectangle, then opposite sides are congruent, so A squared plus B squared equals C squared. We just proved the Pythagorean theorem. This means it's true. We can use it anytime. Let's have you guys prove it now. So this is what you've got in front of you. Let's begin by writing up here what the Pythagorean theorem is. And again, it's got to have a hypothesis and a conclusion. So give yourself the right triangle picture with A, B, and C, and show that then, as a result of that, you can say that A squared plus B squared equals C squared. Now, in this case, we're going to take this original triangle and I'm going to copy it and paste it here after a transformation and rotation. And then I'll copy it again and rotate, and put it here. Copy it again, rotate, and put it here. One more time. And I create this shape. Just like we did before, let's put a star here and a circle here. Circle, star, circle, star, circle, star. We built this so that this is continuous, so that this is a straight line. 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 What shape is this? It's a square, right? You know that because it's got 4 right angles and each of the sides is the same length. What is the side length here? Almost.
A plus B.
A plus B. We're adding those 2 lengths together. This is A plus B. This is A plus B. This is A plus B. So if I wanted to find the area of this shape, knowing it's a square, I would say that it's length times width, which would be A plus B times A plus B. And you may remember from algebra, gentlemen, you may remember how to FOIL this or distribute. We'll do A times A is A squared. A times B is AB. B times A is BA, but we can call that AB. B times B is B squared. So this all comes together, these two combine, and we end up with A squared plus 2AB plus B squared. That's the area of this shape. Can we all agree to that? Okay. Just going to leave that alone there for a second. Now I'm going to take the exact same shape and I've just colorized it differently because I don't want to treat it as one big shape. I want to treat it as 5 different shapes. In other words, if I can find the area of all the parts. So what are the areas or what are the parts? Can we agree that ABC and ABC, there's 4 of these little right triangles that are all congruent? So we're going to take 4 times whatever the area of the right triangles are. And we're going to add the area of this. What shape is this? A square or a rhombus? It's definitely a rhombus. Is it also a square?
Yeah.
Good. The circle, right. We can do that thing again. We'll do that in a minute. And so this would be the area of that shape, whatever it is, which we're going to say is a square. How does one find the area of a triangle? Base times height, which have to be perpendicular to each other, divided by 2, or 1/2 A times B. And because we're saying this is a square, we can just find the area by saying C times C or C squared. What is 4 times 1/2 AB? 2AB plus C squared. And this is the area of the same shape, but by parts. Since it's the same shape, shouldn't this and this be equal? Therefore, I can take what this is equal to, A squared plus 2AB plus B squared, and set it equal to what this one's equal to by substitution. 2AB plus C squared. Now what? Subtract 2AB from both sides. And I'm left with A squared plus B squared equals C squared. Now the little kind of star and circle way I did this is a little bit loosey-goosey. So let's be a little bit more clear that in fact angle 2 does end up being a right angle. So this is in fact a square here. What do we know about angle 1 and angle 4? They're congruent, right? In other words, the measure of angle 1 equals the measure of angle 4. Why? Well, it's really CP/CTC. I made the triangles congruent, so the corresponding parts are congruent. What do we know about 3 and 4? Measure of angle 3 plus measure of angle 4 plus 90 equals what? 180. And that's the triangle angle sum theorem. And then I can subtract 90 from both sides. So I get the measure of angle 3 plus the measure of angle 4 equals 90. That's subtraction property of equality. And since I have 1 and 4 are the same, and 3 and 4 make 90, I can say that the measure of angle 3 plus the measure of angle 1 equals 90. Substitution. I'm going to leave that alone for just a second and come back to say, what about 1, 2, and 3? Do they form a straight line? Together, do they make a straight line? Yeah, we said we constructed this to be straight. Therefore, all three of these add up to 180. And that's because a straight line and angle addition. So now if 3 and 1 make 90, and I can substitute here and say that the measure of angle 2 plus 90 equals 180. Substitution. Subtract, and I get the measure of angle 2 equals 90. Subtraction. In other words, I've just proven that this is 90 degrees. So this central shape is not just a rhombus. This central shape is a square. And thus we can use this area measurement thing. Are you convinced? 5, I now believe the Pythagorean theorem. I've always used it, and it sort of works, but now it's been proven to me. I know it's valid. 3, sort of, I might need a different one. You've shown us 2, but I'm not sure I buy that. I'd like to see another proof. 1, I don't believe it's true. I don't think it's actually a theorem. Okay. Hands down. So it turns out that over the generations, proving the Pythagorean theorem has been sort of a feather in people's cap in higher education, and sometimes a bar that they had to achieve in order to get a college degree years and years and years ago. So there are actually lots and lots and lots of these things, proofs of the Pythagorean theorem, somebody taking a different slant at it. What I'd like to do is direct you to a particular website. And the website is called cutthenot.org with dashes. Let me, I wrote it up here somewhere. Cutthenot.org. I'll put this up for you in just a minute. The second part of your homework, in addition to doing this page that you just did, is on the back. I want you to go to this website and I want you to flip through these various proofs of the Pythagorean theorem. And you find one that resonates with you, that makes sense to you, that's different than the 2 we've looked at. And then I want you to, on the back of this piece of paper, draw a representative picture and share in a couple of paragraphs generally what they're doing. You don't have to be exhaustive in the proof, but I want you to show high level why it's true. If you copy and translate these shapes, we make a square. And if you find the area of the square in 2 different ways, then we can see that they're equal. And when you do that, you get a squared plus b squared equals c squared. Okay, so the second part of your homework, which is really all I'm leaving for you to do, is to go to this website, find a proof that resonates with you that you can understand, different than the 2 we've done, and put it on the back of your homework 74 sheet you just worked on. Those both sides will be submitted as Canvas homework for tonight. Any questions? Please be sure that you go to cutthenot.org and not .com. As we discovered some years ago, any guesses what cutthenot.com takes you to? Almost divorce sites. It's kind of funny. Anyway, all right, you've got the period. Go to it. Happy Pi Day.